Welcome to the webinar from architectural design through analysis and calculation to detailing the workflow with Allplan, SCIA and FRILO. A quick organizational note, you can ask questions via GoToWebinar at any time. We will try to answer them during the webinar. However, it may be that we need a bit more time for some questions and we'll answer them afterwards. The reason for the webinar is the recent merger of Allplan, SCIA and FRILO. The aim of this merger is to combine efforts to strengthen delivery capabilities, drive innovation, and offer powerful end-to-end design-to-build workflows. A strong focus will be placed on structural engineering. A new and combined market approach will accelerate the path to data-driven multi-material design and prefabrication, offering a significant productivity advantages for customers. All three companies are part of the Nemetschek Group. Since this webinar provides insights into the various software solutions, I'm not hosting it alone, but together with my colleague Keith Wan from SCIA. Keith will introduce himself in more detail later and demonstrate what is possible with SCIA and FRILO in relation to this workflow. A brief introduction of myself. My name is Maximilian Amendi. Since October 2023, I've been working at Allplan Deutschland, GmbH. As a pre-sales engineer, I support customers and assist the sales team with product presentations. Together with Keith, I will cover the following topics related to the workflow today. So first is uploading the model from Allplan to Bimplus, then creating the analysis model and exporting an SAF file with the AutoConverter, then calculating the analysis model in SCIA and FRILO, reinforcement planning in Allplan based on the results from SCIA and FRILO, which transferred back to Allplan in the form of an SAF file. On this slide, you can see the complete workflow illustrated. As mentioned earlier, we start in Allplan, then move on to the AutoConverter and Bimplus. Subsequently, the calculation is done with SCIA and FRILO, and finally the reinforcement planning in Allplan is carried out based on these results. Okay, so here you can see the initial model in Allplan, which forms the basis for further calculation and reinforcement. The building shown consists of columns, slabs, and beams. This model was chosen because this combination often leads to problems when importing into structural engineering programs. The model data in Allplan are structured through the so-called building structure and layers, which can be activated, deactivated, made visible or invisible for editing in Allplan or later export. Another way to directly show or hide objects is provided by the object palette. For example, the grid, entire floors, or specific components can be shown or hidden here. Additionally, it is possible to assign specific colors to certain components. The model shown here can now be exported as IFC in the traditional way. To do this, go to Teamwork and select Export IFC to initiate the IFC export. Alternatively, the model can also be directly loaded into Bimplus. Simply click on the Upload to Bimplus icon. Select the team and project and upload the model to the cloud. In this case, I've already uploaded the model, so I will skip this step here. Then let's switch to the PowerPoint. Once the model is available in the cloud, the editing process takes place in Bimplus or the AutoConverter. As mentioned earlier, this generates the analysis model. However, let me first provide some general information about Bimplus and the AutoConverter. Bimplus is a web-based collaboration platform. It allows for the cloud-based management of the entire project and model-based communication with other discipline modelers. Multiple model data can be overlaid and also merged in Bimplus. The AutoConverter shares a data storage with Bimplus. Thus, all models stored in Bimplus are accessible to the AutoConverter. With the AutoConverter, the structural engineer can create their own analysis model directly in the cloud and then export the analysis model into the SCIA format. A few words about the SCIA format. So the SCIA format, also known as a structural and analysis format, is another open BIM format supported by many software providers. It is based on an Excel file and contains all the relevant information for the structural engineer. This makes the file format easier to edit as well. And yeah, that was a brief introduction. At this point, I would now proceed directly to Bimplus. Yeah, here you can see the home screen of Bimplus. At the top are the corresponding projects. In this case, the project webinar Allplan SCIA FRILO, where the model was previously stored. On the left side, there is the option to invite various members and assign them appropriate access rights. These can, as mentioned earlier, also be external modelers. Below that are the models that our project participants can upload in IFC format. Additionally, there are documents. Bimplus allows files to be stored in almost all common formats, such as PDF, Excel, PowerPoint, and so on. These can then be linked directly to the model. Next, I would briefly switch to the model area of Bimplus. On the left side, you can now see there are many additional functions that Bimplus offers, such as revisions, collision, and model checks. I won't go into further detail on that at this point. However, what I would like to briefly show is the possibility of issue management, which, in my opinion, provides significant added value in terms of the workflow because it enables model-based communication between structural planning and architecture. I've already prepared such an issue in this case. As you can see, I can locate constructive concurrence or errors in the model in this way. This issue will then be displayed in Allplan exactly in the same way as shown here. Just let me switch back to Allplan briefly. Here you can see exactly this issue that I created on Bimplus, and the notes are thus also directly available to me while modeling in Allplan. The issue is located in the issue management palette or area. which is on the left side in Allplan. So that's all about issue management and model-based communication possibilities via Bimplus. In the next step, I would like to generate the analysis model via the AutoConverter. So to start the AutoConverter, I just return to the start screen of Bimplus. To start the AutoConverter, just click on the icon on the left side. Once the AutoConverter has started, there in the top left corner are the models, where I can now see all the models that are in the Bimplus project. Using the eye symbol, I can then display the corresponding model. A continuous analysis model is to be derived then from this one. To do this, I start the function convert structure to analysis model. Here in the first step, I can select which model I choose as the base model. In the second step, the model cleaning takes place. After that, the individual components are detected and converted into 1D or 2D elements based on previously selected settings. Finally, these are all gen into a continuous model. So after selecting my model, I begin with the second step and cleaning up. Initially, all components are grouped and displayed. I can see my beams, columns, walls, slabs, stairs, and foundation, also as the grid. By using the trash can icon, I can hide these groups without deleting their components. In this way, I can also easily remove overmodeling, such as in this case, the slabs. It is also important that the data is not deleted, it's only hidden and no longer considered in further processing. Finally, I would like to remove the steel components. To do this, I simply click on an appropriation component and search for the material. Now all the steel components are displayed and I can hide them as well. This way, I as a structural engineer decide what I consider to be statically relevant or irrelevant. So once the model is cleaned up, I proceed to the recognize settings. Here I can specify how each component should be recognized and assigned a type. Furthermore, I can determine cross sections or add materials. To do this, I simply click on the material and choose the appropriate material for the components from a pre-selection. On the layers, I can then filter by specific attributes, such as settings their attribute load bearing to true. Once satisfied with the settings, I proceed to recognize the model in the next step. This means that the components are now processed according to the settings made earlier. In the next step, the goal is to origin the model with the corresponding originment settings. Here, similar to the recognize settings, I can set specific parameters regarding the system line and eccentricity. In this example, the beams are intended to have their system line at the top. Finally, the model is algined and merged accordingly. He merged model can then be saved in the cloud with the project by saving it. This model becomes available again in Bimplus and the AutoConverter. So as you can see, when I switch back to the model area, both models are now available to me, and I can hide and show them using the icon, just like at the beginning. So to export the model in SAF format for further analysis, I initiate the export to SAF file function. After selecting the model, I have additional options here, such as the version or the coordinate system. I can choose the coordinate system to match the one used in my structural engineering program. So finally, I only have to assign a file name and receive my SAF file for further processing. At this point, my part is then completed for now, and I will pass the floor to Keith, who will now demonstrate how to calculate the analysis model generated just now in SCIA and FRILO. So go on, Keith.
Thank you, Max. Hello everybody, my name is Keith and I am a customer service engineer in SCIA. Today I will be showing you how the model data you saw earlier can be used to create structural analysis models in both FRILO and SCIA Engineer. You will also see an example of how we can give engineering design information back to the BIM technician. Firstly, I'm going to give you an overview of the workflow between Bimplus and FRILO. Max has already shown you the Allplan model. He has also transferred that model to Bimplus. Then you saw how the structural analysis model was prepared using the AutoConverter, which Max has made available to me via a SAF file. This can be imported to FRILO FBC, otherwise known as our BIM connector program, and from there you can prepare a model for engineering design using other FRILO design applications. Shortly, I will show you an example of this process by transferring the connector model to FRILO slab design program. Then we'll export an example reinforcement design to an ASF file, which Max can then use to detail the reinforcement. As a side note, it's also possible to import directly from Bimplus, however that won't be shown today. Instead, we will be focusing on the SAF file method. So now, let's take a look at this in action. As you can see, the SAF file has already been imported into the connector program. Here, we can prepare parts of the model for individual FRILO design programs. Today, we'll focus on a slab design. With that in mind, and something that frequently occurs, we need to do a little bit of work where the slab is supported by a wall. The reason why is so that the effect of the wall openings are correctly considered during the slab analysis. In the program, we have two options. Firstly, we can split the wall into only wall strips. This considers only the wall strips on either side of the opening. Effectively, this means the wall section above the opening is ignored. so the slab is not supported over the wall opening during the analysis. Alternatively, you can split the wall into individual members. This way, a lintel beam spans between the adjacent wall strips, and the support provided by the lintel beam is taken into account during the slab analysis. When using this option, you can specify some limiting dimensions that the program considers when creating these lintel beams. Now that this is set up, we can pick a floor slab to design in FRILO PLT, or otherwise known as the slab design program. For this demonstration, there are no free loads on the floor slab, and because of this, we can simply transfer one of the floor plates to the slab program. To do that, I select one of the slabs, then go to Export, and select Slab Dimensioning by PLT. Now, we define how support stiffnesses are calculated and transferred. We can simply set support points or lines as rigid, or we can calculate a spring stiffness based on the supporting member's properties. If there had been additional loads in this connector model, then we could have transferred those via this setting. Auxiliary constructions can be used to automatically create lines in the slab model. These lines act as drawing aids if we intend to manually create other loads in the slab model. Now let's complete the transfer. You might have noticed the plate program started automatically, and we can see the complete slab geometry has been imported. If we look at the load cases, we can see one permanent load case has already been created. Now I'm going to create a new load case for variable loads, and let's call that load case Q. To keep things simple, let's create a new variable area load over the entire slab, and we'll set the load value to 2.5 kilonewtons per meter squared. Now I'll switch to the permanent load case and add an additional 0.5 kilonewtons per meter squared. So now we go to the calculation. Before running the analysis, we can see the load cases that will be calculated and the partial factors that will be applied. And then we can start the calculation. When the analysis is finished, the results are automatically displayed. We can use the superposition and load combination settings to switch between results. And we can change the result type using the toolbar on the right. Currently, we are looking at the required reinforcement in the bottom of the slab. And if we zoom in, we can see that the maximum required is approximately 3 cm squared per meter or 300 mm squared per meter. And we can also show a similar design result for the upper reinforcement. As you can see, there are other result types available, but now we will carry on with the demonstration and we will transfer this design output to Allplan. To do that, we simply go to File, Export, and Allplan. Here, we save the results as an ASF file, which I can send to Max for the reinforcement detailing. So that's all I wanted to show today in regards to FRILO. Now let's have a look at how this design workflow could work with SCIA Engineer. Very similar to FRILO, we can import Max's model into SCIA Engineer, but this time we'll download the prepared SAF file directly from the Bimplus platform, and then import the analysis model to SCIA Engineer. We can then add loads and boundary conditions like supports to be able to run an analysis. And of course, use the engineering design tools in SCIA Engineer. Then, we can export the design results to Allplan via an ASF file. Okay, so let's go to SCIA Engineer. You can see SCIA Engineer is already open. And now I'm going to create the analysis model via Bimplus. Here, I need to select the appropriate team, project, and model settings, and then download. Now I can import the model geometry. So here we are. We have the same model you saw in the earlier demonstrations. You can see that FE members have been created with material properties and thickness values, taken directly from the Bimplus model. Because we imported the geometry, a lot of the modeling work has already been done, but we need to add support to be able to run an analysis. To keep it simple, I'm simply going to add one surface support to the ground floor. You can do that via the input panel and then select surface support. As you can see, there are some predefined subsoils to select from. I'll just take this one, for example. Now, I'll add some nominal lateral stiffness to this subsoil, otherwise the structure can freely slide around. Now, let's apply the surface support to the ground floor slab. If we view the load cases in the model, we can see that a self-weight load case is already there. And that is calculated based on the structure's geometry and material density. And we can rename this load case to SW, short for self-weight. Now let's create a new load case. I'll change its properties so that it's considered a variable load case, and I'll rename it to QK. To add loads, I first need to make sure that load case QK is active. Now we can add loads to the floor slabs. If I select one member, I can select other members with a similar property. So, for example, I select the ground floor and I can expand my selection to include all other 2D members with the plate type. Then I can add a surface load to all the selected plates. Let's set a value of 3 kilonewtons per meter squared. Before we start the analysis, let me show you the load combinations. As you can see, 3 combinations have been created automatically. There is a ULS set B combination, SLS characteristic, and SLS quasi-permanent. All of them will automatically generate individual combinations. Those generated load combinations will be factored accordingly. So, for example, if we explode the ULS combination, we can see that it contains 4 load combinations, each with different load factors. The envelope combination would give us the minimum and maximum result across all of these load combinations. Let's delete those exploded load combinations, as they are not really required, and let's run the analysis. Okay, the analysis is done, and we can see it has finished successfully, and we can view the results tab. In here we can see if any warnings or errors. Before designing the reinforcement, let's have a quick look at some of the available analysis results. Firstly, you can get a quick understanding about the calculation status by using the calculation protocol. Here you can see if there is equilibrium in each load case. Now let's see if the deformed shape is what we expect. We'll select all members and show the results just for the self-weight load case. For me, this deformed shape looks reasonable given the conditions, as well as the maximum deformation value. If you like, you can also view the deformed shape for one of the SLS combinations. let's move on to the 2D internal forces. For a clearer picture, we'll just focus on the first floor slab. I'll set the selection to current and select combinations and look specifically at the ULS combination. And we'll leave the value set to mx, i.e. moment along the x-axis. Okay, so now we have the mx bending moment results. These are the moments spanning between the main floor beams. We can also view the moments in the y-axis, i.e. my. Now let's take a quick look at the 1D internal forces. We can start with an overview of all 1D members. Using the envelope ULS results, we'll set the extreme to global, so we'll only see the values for the worst members, and we'll view the axial force N. With these settings, we can quickly find the most highly loaded members in terms of axial force. We can immediately see the red text shows us the most compressed column, and the blue text actually shows the downstand beams have some tension force because they are working with the slab. We can see the equivalent tabular results by going to the report preview. Here we see the critical members for each type of internal force. For example, the maximum compression force is the same as the graphic seen, but there's additional information such as the critical load combination. Now, let's look at one column stack, but in more detail. We'll adjust the result settings to show the worst results per member. Now we can see the axial force diagram for the full column stack. We can make the graphic scene more readable by hiding unwanted members. You can easily and quickly do this by using the visibility settings. So here we have the same results, but with a much more readable graphic scene. Once you're done with this view, those hidden members can be quickly brought back. Now let's switch to the concrete design menu, and we will go directly to the 2D reinforcement design. Again, we'll focus on the first floor slab, but before we do anything, I'm going to hide the unwanted members. Now let's design for the ULS results, and we'll calculate the required reinforcement in one of the bottom layers. What you see now is the required reinforcement in the bottom of the slab, specifically for the bars running left to right on the screen. You can also see the background calculations via the report preview. Here we have the most detailed report type. You can see diagrams, formulas and references to the design code. This way you can gain some confidence in the design. If you prefer the report to be more concise, you can choose the standard output level. Here you will see a single page design summary. For completeness, we can quickly view the bottom reinforcement in the orthogonal direction. Similar results are also available for the upper reinforcement layers. However, so that we can save some time, I won't show them today, but I can assure you the design tools work pretty much in the same way and along the same principle. To finish the demonstration, let's export these reinforcement results to an ASF file. Let's give this a memorable name and save the file. In practice, an ASF file can easily be shared via network or email. Alternatively, I could also upload to Bimplus. However, my part of the presentation is finished now, so I'll pass you back to Max for the final section.
Yeah, thank you, Keith. Now I will proceed to the last part of the workflow, which involves the ASF file and reinforcement planning in Allplan. This means importing the results from the structural analysis into Allplan and subsequently using them for reinforcement planning. Before I start with the reinforcement, I first derive a section and a slab underside view from the model. To do this, I reduce the model to the first floor slab using the building structure and create a partial model with an appropriate designation to generate the corresponding formwork and reinforcement planning. So first I generate a vertical section with the corresponding labeling. I then place this section below the model. Next, I narrow the section in terms of height using the grips so that only the slab and a bit of the column are visible in the section. So next I generate another section, which is a slab underside view. The height of the section area can of course be specified when creating the section. I then define the section area and label it accordingly, placing it again on the partial model. Thus, I now have the model data at the top, a vertical section of the slab, and finally the slab underside view. So now in the next step, the FEM data or the ASF file is imported. This is done via the import FEM data icon under Teamwork. Here I select the ASF file created by Keith, place it on an appropriately empty partial model and start the import process. The data is now available on partial model 100 or 101 in the correct position and can be considered for reinforcement. The partial model with the data does not need it to be activated or be visible. So to begin with the reinforcement, I switch back to the partial model with my views and sections. Here under the reinforcement task, I start the FEM reinforcement IMAG function to access the results. Various parameters for the reinforcement can be set here, such as the position, type, bond area, and whether the color grading adjustment should be automatic or manual. The corresponding minimum and maximum AS value are also specified. Confirming with OK starts the function, and the screen is split. On the left, the model and sections are visible again, and on the right, there are FEM results. So the corresponding reinforcement can now be placed in this case, field reinforcement. The reinforcement area, reinforcement height, and openings are then specified. This is followed by confirmation with OK. And so next, the mat can be selected and further parameters can be determined, such as the reinforcement direction, and also confirming it with OK generates the reinforcement. So the colors indicate whether a sufficient reinforcement has been placed or where more reinforcement is needed. Finally, I can add supplementary reinforcement as shown in this small section. Here again, I can then see how the color image adjusts according to the reinforcement. And so with this technique, I can always directly see if there is enough iron in my concrete. And yeah, in the next step, I just want, in conclusion, I would like to briefly summarize what has just been shown. So the workflow begins in Allplan with the architectural design. Subsequently, the structural engineer defines their analytical model using the AutoConverter and Bimplus. This model is then calculated in FRILO or SCIA. After the calculation, there is the possibility on Bimplus to locate constructive errors directly in the model using the issue management. Once all issues have been resolved, 3D reinforcement planning based on the FEM results can commence in Allplan. And finally, various plans can be derived from this model. So from this workflow and approach, the following advantages emerge. First, comprehensive solution from architecture to analysis and detailing. It's also collaborative coordination of detail based on one model. And design and engineering of reinforcement based on an integrated analysis. And so on. It's an open BIM workflow. Yeah, so thank you for your attention. And we will, as I said at the beginning, we will answer any remaining questions as quickly as possible. And otherwise, I wish you a pleasant day. Thanks for your attention and bye-bye.